this is Dr. Raghuram Mohan Reddy, Associate Professor, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. The course name is Unconventional Machining Process. The topic is Definitions and Terminology of Module 1, Part 2. Already in the previous presentation, just I have mentioned that in the Module 1, we have divided the definitions and terminology in two different parts. So the first part is in the previous presentation. Next, the rest of the things that we have discussed here. Okay. So at the end of this session, students will be able to understand the definitions and terminology of non-traditional machining process. So of the things that we have covered in the previous presentation. So the rest of the things that we are going to discuss in this. Okay. Thank you. Right. Process parameters. Okay. Surface finish tolerance. Okay. So quality of the machined surface, including smoothness and texture. Okay. Surface finish is the important process parameter. Okay. So here quality of the machined surface, including smoothness and texture. Okay. Right. Tolerance. Acceptable deviance from specified dimensions, crucial for precision parts. See, we already know that the manufacturer cannot manufacture exactly, okay, as per the designs, but it is acceptable to certain tolerance. Okay, suppose let us say the diameter of the hole would be 10 mm. Okay, the manufacturer exactly cannot make with the 10 mm diameter, whether it may be 10.0005 or 9.999 like that. Okay, so every hole may not have the same dimensions, and again at the same time no hole may reach the same let us say given exact integer dimension 10. Okay, so here the tolerance will play a predominant role. Okay, we cannot give high tolerance to the all the parts. Okay, why? Because when the tolerance is high, then the expensiveness would be more. Okay, tolerance range. Okay, next, production requirements, batch versus mass production. Okay, right. Choice of process depending on production scale, such as prototype versus large scale manufacturing. Okay, next, prototype production. Special considerations for initial prototypes, including cost and time constraints. Okay, so here production requirements, batch versus mass production. Choice of process depending on production scale, okay, such as prototype versus large scale manufacturing. Right. Prototype production, special considerations for initial prototypes, okay, including cost and time constraints. Okay, right. Key terminologies, okay, surface integrity, dimensional tolerance. See, in all the processes, dimensional tolerance and surface quality or surface integrity are must. Okay, right. Let us discuss surface integrity. Overall condition of the machine surface, including mechanical, thermal and structural aspects. Okay, so here with respect to various conditions of the machine surface are important, including mechanical, thermal, and structural aspects. Next, dimensional tolerance. Permissible limit of variation from a specified dimension. Okay, so it can be permitted to a certain limit. That is nothing but permissible limit of variation from a specified dimension. That is nothing but dimensional tolerance. Already I told you. Okay, see, let us say for the alloy wheel of an automobile. Okay, let us say it is 1 feet, or let us say uh, any alloy wheel or something. Let us say 0.5 meters. So for automobile, it may be 0.5 meters plus 1 mm to 2 mm. Okay, that can be allowed for, let us say, tractors and all this. Suppose if you take any rotating element in the aeronautical parts, we cannot give that much tolerance, 1 mm or 2 mm. Okay, that is very difficult to give that much tolerance. Okay, so even in automobiles also, we can give tolerance in terms of microns. Okay, so if it is 0.5 meters, then 0.5 meters plus 0.001 mm or 0.5 mm, okay, to the maximum extent. But for aeronautical parts, we cannot give tolerance 0.5 mm, 0.75 mm. Okay, so it should be below that. So dimensional tolerance will be permitting based on the application of the parts. Okay, where we are using is that important. Materials and their applications. That's what I'm saying. Advanced materials. So ceramics, composites, superalloys. Ceramics, hard, brittle materials used in applications requiring high wear resistance and hardness. Okay, so usually we use ceramics, which are hard, brittle materials used in applications requiring high wear resistance and hardness. Okay, so even if we have some sort of what is that called resource, okay, to use these ceramics, we should not use, that means not resource, availability of ceramics, okay, freely we cannot use everywhere. Why? Because sometimes we need some ductile property too. Okay, so here ceramics are very hard and brittle materials. Okay, so ceramics, hard, brittle materials used in applications requiring high wear resistance and hardness. Okay, right. Composites, materials composed of two or more different substances to achieve enhanced properties. Okay, for example, carbon fiber composites. Okay, so here, in order to have enhanced properties, we have to use composites. Okay, so composite materials are composed of two or more different substances. Okay, right. Superalloys, high performance alloys designed for extreme conditions, often used in jet engines and turbines. So superalloys are very wear resistant and heat resistant materials. Okay, see, that's why we use in jet engines and turbines. So in turbines, see, if you take water turbines, hydraulic turbines, so high impact of the water particles, it will damage. Okay, so here only superalloys only can resist that high impact by the water. Similarly, in jet engines also, because of the high heat and high wind power, whatever it may be, we have to use super alloys. So otherwise, what will happen? It will be damaged. Okay, right. Next, application areas. Aerospace. Okay, components such as turbine blades and structural parts requiring high strength and precision. Okay. Next, medical devices. Implants and surgical tools requiring high precision and biocompatibility. Okay. Electronics. Micro machining for semiconductors, printed circuit boards, PCBs, and other electronic components. Okay. So application areas are aerospace, medical devices, and electronics. Okay, right. Aerospace, components such as turbine blades and structural parts requiring high strength and precision. Right. Medical devices, implants and surgical tools requiring high precision and biocompatibility. Okay. Electronics, micro machining for semiconductors, printed circuit boards, and other electronic components. Okay, right. Key terminologies: super alloys and composite materials. Okay, alloys engineered to withstand extreme temperatures and stresses. Okay. Excuse me. Right. Super alloys. Alloys engineered to withstand extreme temperatures and stresses. See, already we have discussed that in turbine blades, okay, and aeronautical wings, etc. See, some parts are very heat resistant and stress resistant. Okay, so where we have to use super alloys. Okay, so for other normal bodies we can make use of our general alloys, but for super alloys significance is that to resist high temperatures and stresses. Right. Composite materials. Materials made from combining multiple materials to achieve desirable properties. Okay. So sometimes only ferrous, okay, only copper, only zinc may not solve our purpose. Sometimes we have to combine these things. Okay. So carbon fiber are the examples of the composite materials. Next, material removal phenomena. Erosion. Okay. Now definition and mechanism. Let us see. Okay. Definition means removal of material through impact by abrasive particles or fluid jets. Okay. And mechanism. Abrasive particles strike the material surface, causing localized material removal. Okay. Erosion. Removal of material through impact by abrasive particles or fluid jets. And mechanism. Abrasive particles strikes the material surface, causing localized material removal. Okay. See, there should not be any heat affected zone or the zone which is subjected to some stress, that is nothing but induced stress. Okay, so when we remove the material, it should be surgical or localized. Okay, right. Vaporization, definition, mechanism. Okay, again, along with vaporization, electrolytic dissolution is other parameter. First, let us discuss the vaporization. Okay, definition: conversion of solid or liquid material into vapor due to high energy input. Okay, and mechanism: material absorbs thermal energy leading to its vaporization. Okay, next, electrolytic dissolution. Definition: removal of material through electrochemical reactions in electrolyte solution. Okay, mechanism: electric current dissolves the material at workpiece surface. Okay, right. Key terminologies: aeration rate and vaporization temperature. Okay, these two are the important terminologies. Okay, the rate at which the material is removed during erosion processes. Okay, that is nothing but erosion rate. The rate at which material is removed during erosion processes. Okay, it means it is time based. Okay, vaporization temperature: the temperature at which a material changes from solid or liquid to vapor. Vaporization temperature is that the temperature at which a material changes from solid or liquid to vapor. That is vaporization temperature. Right. So these are the references associated to this presentation. So however, before conclude, let me summarize. Okay, so here process parameters, surface finish, okay, and tolerance. Okay, and production requirements, batch versus mass production. See, sometimes batch production is required and sometimes mass production is needed. Okay, so choice of process depending on production scale, such as prototype versus large scale manufacturing. Okay, right. Again, second one, prototype production. See, special considerations for initial prototype including cost and time constraints. Okay, right. And key terminologies: surface integrity, dimensional tolerances. Okay, and materials and their applications: advanced materials such as ceramics, composites, and superalloys. Okay, see, usually we should not use, though the materials are available to us. Okay, so sometimes ceramics may be fit to the particular applications. Sometimes we have to use composites. Sometimes, particularly aeronautical applications, and where the stresses and high temperatures are there, where we have to go with superalloys. Okay, and the materials, particularly in aerospace, medical devices, and electronics industry, are very particular in precision. So we have to use some particular materials with some particular operations. Okay, here already we have discussed superalloys and composite materials. Okay, material removal phenomena that we have discussed. Okay, definition and mechanism. Okay, vaporization, definition, mechanism, and electrolytic dissolution. Okay, right, we have done this. And erosion rate and vaporization temperature, which is very important, the temperature at which material changes from solid or liquid to vapor. Okay, so these are the references. With this, I'm concluding this.
Like, share and subscribe. Hit the bell icon for more updates.